first demonstration, we're going to try and show parabolic motion. So I'm going to use a heavy object, low surface area, so it has minimal friction, and I'm not going to throw it very high, so we get hopefully a pretty clean parabolic arc. One more time, do a little higher.
Okay, so I've taken the short throw video and I've taken the first throw out of that video and put it into the Kinovia software. This is actually the second time I'm doing this because I found out that I had rotated the video and then resaved it, and the software that I had used to edit the video apparently had added dead frames into the video, and so when I pulled it over into Excel, there was these weird motion artifacts. And so I've done this again to try and get a slightly better export out of this. But you can see here, I have the path of the weight marked up during the throw. And I'm actually playing this back at quarter speed. So it's, takes quite a bit longer for it to go through, but the throw is about a second long. I'm going to show you guys how to use this software in a future video, but just for now, note that I've taken the throw and I've marked the path of the weight throughout the throw. I'm going to export that into Excel for us to actually look at the raw data. So now we've got all of our data from the short throw put into Excel, and I'm just going to go through a few things that we've done inside here. This is actually the raw data from the Kinovia software, and it's in pixels, so it's not in units of feet or inches or anything that we really have that's useful. So I measured the position of my head and an approximation of my height, accounting for some correctional factors and things like angle and stuff like that, into here so that I can transform the units of pixels into the units of meters. And again, here it's important to note that the more accurate your transformation here is, the better the data is going to be. So if you have something of a known length inside your frame, that's going to work well. You need to know what the orientation of that part is too. So some of the inaccuracy here problems here is, but I'm probably not standing perfectly straight. My head's not perfectly straight up. My feet might not be directly underneath me, and all those different kinds of things. So the better job you can do setting it up, the better it's going to be. But as an example, it doesn't really matter that much. Again, the point here is to kind of demonstrate how this works, and getting the data out of it is kind of less critically important. So here I've transformed the coordinates from pixels into meters. The origin for this, basically 0, 0 point, is at the base of my feet, and so this kind of starts off around my height and then goes up from there. And then I've used my forward difference approximation, basically taking the position at time 2, right? Or in this case I'm calling it time 1 because I'm starting at 0. And I'm subtracting that position, or rather the next position from the current position, and then dividing the next time by the current time, just like I did in the PowerPoint presentation intro video. I do that for all the different values of x and y. For velocity, you see a couple of those there. And then I can do the same thing using acceleration. And again, acceleration uses a backwards difference, so rather than using the next value, I use the previous value. And again, that helps with that offset area here, where you can see I lost kind of the last value because I don't have a next one, and then it's because I've lost the first value. So rather than having two missing values at the end, I have one missing at the end and one missing at the beginning. And so you see I have my position, velocity, acceleration data. I've plotted out all of those. So this is the vertical position over time. This is my horizontal position over time. This is my velocity. So this is the vertical velocity all the time. And you can see that this is a nice kind of parabolic arc. And this is a pretty straight line. And this is my horizontal velocity, and you see it's pretty constant. You note there's big steps here, right? So it kind of goes up, down, up, down. The velocity here horizontally is pretty small, so it's pretty close to 0, which is one of the reasons why you're seeing these kind of what looks like a bigger jaunt is that this axis is actually a fairly small range. You notice this one's going from 4 meters per second to negative 4 meters per second. This one's going from 0 to 0.4 meters per second. Also, that our data is in pixels, right? So we have these pixel values over here. So the smallest distance that we can measure is 1 pixel. And that looks like that corresponds to about 0.05 meters of distance, right? So that's why we have these kind of bigger chunks, right? We also have our time resolution. So our time resolution and our distance resolution is going to affect these velocities and actually have these mislabeled. This should be meters per second, and not meters. I labeled them correctly over here, but not on my axes. So let's just fix that real quick. Making sure your axes are appropriately labeled is a really important thing to do. Also, to save time, what I've done with these is like I kind of copied and pasted them and then moved them around and did that. That's why these are all wrong. But easy to fix. Just make sure that you fix them before you publish these anywhere important. There we go. So I have my horizontal velocity and my vertical velocity. Again, horizontal is small and relatively constant, is decreasing a little bit, it looks like, but not very much. And then I have my vertical acceleration, and you can see my vertical acceleration is somewhat constant, but there is quite a bit of noise here. It's around, somewhere around -10, should be something close to -9.8. And I actually kind of fudged my height value here to make this a little bit closer to 9.8, because I know that's what it should be. -9.81 meters per second squared is the acceleration for gravity on Earth at sea level. So it should be something close to that. And then again here, the horizontal acceleration, since there shouldn't be any force acting on this, should be close to 0. And you see it's pretty close to 0 most of the time, but there is some oscillations around that. A quick note on these oscillations or this noise inside this data. Because we're starting with position, this is what we're recording on. This is kind of the highest quality data. Every time we take a derivative, right, if there's a little bit of noise inside this data, that noise gets amplified in the derivative because the noise is going to be at the frequency of the recording. So if I have a very high frequency recording and I have a little bit of shift, right, since the delta t on that derivative, in this case, kind of the denominator in my velocity and my acceleration calculations, right, this t2 minus t1 or whatever it is, if that value is very small and there's a little bit of noise, you can get a very large kind of jump, like you see in this chart here and in these charts here, because of that. So one of the things we do is we can actually filter this data to kind of smooth that out and get rid of some of these jumps. But the higher order derivative that you take, the more significant those are going to be because of the kind of the properties of the derivative. So keep that in mind. If I were to go to jerk, which is the derivative of acceleration, then this would get even more significant, and the amount of filtering would be more. Now, if you're going to filter, you also need to have more data because you're effectively decreasing the frame rate when you filter. So, if I really wanted to get a good measure of acceleration using this kind of video-based motion capture, I would want to use a higher frame rate camera, so that way I could filter the data and still have reliable results, right? So that's one thing you need to take into account. We're not going to go into filtering algorithms to try and improve this in this module, but it's one of the things that we cover as part of the curriculum at FGCU in the Biomechanics course and in the signals courses. So, all right, moving on to the next thing.